All right, so in section 6.5, we learn a new number, which seems strange that, that there might be a number that you're completely unaware of. But the number that we learn in section 6.5 is the number e. And this calculator has e located in a couple places, one to use e with an exponent and one to use e just by itself. I just want to show an e on my calculator right to the left of the answer key. If I kind of blow this up a little bit, you'll hopefully see the you can't see it right down there. There's a key that the x times 10 to the x key has pi on the left top and e on the right top. And if I hit the alpha button and that key right to the left of the answer key, it gives me e. And if I hit equals, it might just say e. No, it doesn't. It gives me the decimal equivalents for e. So e is similar to pi. Maybe that's why it's on the pi button. Like if we did shift pi, if I make it into a decimal by hitting the SD button, I get 3.14159. That's a number that gets a symbolic representation that you might be used to. But e is another number that gets a letter name. So it's a short, the e stands for 2.718281828, and its decimal expansion goes on forever. And my calculator almost makes it look like there's a pattern to e, but there isn't a pattern. It's an irrational number, and if I started adding more decimals than my calculator can give me, I'd find out that there's no pattern, and this decimal goes on forever without ending or repeating. And because we're in a logarithms chapter, we have logarithms base e. So e is a number, and the log base e is often called the natural log. Natural kind of maybe being the root word of nature. And in the last section, where I said we can use logarithms to answer when questions. Specifically, when we're answering when questions with logarithms, like when will the millionth person get the flu, or when will an oil slick size be 2,000 square miles. Log base e is normally the base that we use to solve those types of questions. Things that happen in nature are generally what we use log base e. And log base e happens so much that there's a shorthand for it. So if I wrote, if I asked you to calculate the log base e of, I'll do a nice easy number, it's still going to give me a horrible decimal though. If I want to compute the log base e of 10, I can certainly do that using my calculator skills that I have already. If I hit the log with the base and hit the alpha button and get the e in there and then do 10, log base e of 10 is about 2.3025855092. That wasn't really a nuisance to enter, but there is a shorthand for log base e. And the shorthand for log base e will make it quicker on my calculator when I'm working with it. So it's a really quick thing to write, but not that much quicker. The shorthand is ln. Log base e is that's very clear that the base is e and the argument is 10. If someone writes ln, which I usually read as natural log, this is the same as the log base e of 10. So if I did the ln of 10 on my calculator, that's going to calculate the log base e of 10, and I don't need to type the e. So it speeds up the process a little bit, so the number is exactly the same. And that's going to be the case for any number. If I did the log, if I did the log base anything, like the log base e of 125 gives me 4.828. If I do the ln of 125, I still get the same 4.828. So log base e and ln are interchangeable. ln is shorthand for log base e, and more often than not, I like using the shorthand, but there's going to be some times when I'm doing algebra that if I don't see the base, it makes it harder to do what I need to do. So I'll interchange between log base e and ln kind of as it suits me. The strange thing about e is how it was created. A guy named Euler created it the better part of 300 years ago now, and I'm not sure why he did what he did, but technically e, we'll say, is this. We're not in a calculus class, so I'll dispense with the calculus symbols. But e is that 1 plus 1 over infinity to the infinity power. If you look at what I have for e on my what my calculator said e was when I did alpha e, my calculator said e was that. If I can't use infinity on my calculator, but I can get another approximation for e that's going to be close to that by changing this infinity to a big number. So if I wanted to approximate e and my calculator didn't have an e button, I can replace that infinity with a really large number. The larger the number, the better the approximation. Without a calculator, I still wouldn't do it. So for instance, if I did this, e, I'd say it's approximately, if I did 1 plus 1 over 1,000 to the 1,000th power, it's not going to equal that, but it's going to match up to e to a bunch of decimals. If I did just this, parentheses 1 plus fraction 1 over 1,000 to the 1,000th power, if you look at that, it's 2.716. I'm good to 2 decimal places. If I increase that 1,000 to 10,000 and do 1 plus 1 over 10,000 to the 10,000th power, now I'm matching up 2.718. I'm matching up to 3 decimals, what my calculator says e is. If I bump that 10,000 up to 100,000, by adding zeros, then I match e 2.7, then I match e to 4 decimals. So the bigger the number I put in for the infinities, the closer I'm going to match my calculator's approximation to e. The nice thing is we don't have to worry about that. We have an exact approximation that my calculator wants us to use by just hitting the alpha e button. Normally, like if I asked you what pi was, normally a lot of you would say 3.14, even though it's 3.141592654, and there's more numbers after that. If you saw Life of Pi, you watch the kid spit out, I don't know, thousands of numbers in the pattern for pi. But normally when somebody asks me, what is pi, mathematically I say 3.14, and then if somebody asks me what e is, I usually say it's 2.72, and I round this to 2 decimal places, just kind of like pi is generally rounded to 2 decimal places. 2.72 is probably the most common if you asked a mathematician what is e about, as a decimal, and 2.72 is the number that is kind of kicked around more often than not. So this whole section is kind of a repeat of, there's nothing new in this section. There's a bunch of calculator problems because for e's and ln's, mostly I can't do them in my head. Mostly when I ask you to find e to some power, if I want you to find the natural log of some number, it comes out to a really unpleasant decimal, and which means there isn't really an easy way to do it without a calculator. So there's a lot of calculator work in this chapter. And then we do some graphing again. The ways I get my tables set up are going to be the same as we've already done when we graphed functions that had x in the exponents and logarithms. So there won't be really new rules. And we're going to do some money word problems again. And there's going to be a new formula for the money word problems, and I'll get to that in a bit here. So let me just kind of jump into this a little bit. And again, back in the day when I wrote this, which really is not that long ago, calculators really fought the heck out of you and made it hard to do certain things. And e's were used to be just disastrous, but on my calculator now it's going to be easy. As I mentioned when I was talking, there's two places that have an e on my calculator. On this 10 to the x key, if I wanted an e without an exponent, I could activate the alpha and hit that. But if you see on top of the ln key, there's an e with an exponent. If I have to hit the shift button and the ln key, which is right under the log key we've been using, that gives me the luxury of typing an exponent in along with my e. It's very common to have to include an exponent with the number e, and my calculator knows how to do that quickly. So I hit a shift and ln. This problem wants me to round this to 2 decimal places, and I'm going to round the 8 up to a 9 because of the 5 after it. So I'm going to put squiggly equals because this is an approximation, and I'm going to say e to the 3rd power is about 20.09. For the next one, to do e to the -2 power, I hit the shift key, the ln key, and then -2. My calculator tells me this is 0.135. Because the number in the 3rd decimal position is bigger, it's 5 or bigger, I round that 3 up to a 4. And I have the luxury of not writing the 0 to the left of the decimal, but it's probably better to write it. So for an answer for that problem, you could write 0.14, you can write just 0.14. The next 3 problems are ln problems, and the first 2 I could actually do without my calculator, because anytime I ask my calculator to do a logarithm problem, and ln is log base e, if it gives me an answer that is something that's a nice integer, I should be able to do it without a calculator. 6 is easy because we have a rule that if 1 is the argument, the logarithm is 0. And that's just good in general to know. So when I hit ln of 1, because a few lectures ago, or maybe even last lecture, we said the log of 1 is always 0. If I did the ln of 1 on my calculator, I would get 0. Similarly, if I did the log base e of 1, I'd get 0. And ln of 1 and log base e of 1 have the same meaning. Ln is shorthand for log base e. The answer to this is 0. I could put a real hard equal sign if I want to. And then when I was doing logarithms in the last section, I always told you what I was thinking if I could do them in my head. And for this problem, I'm thinking, first of all, I'm not thinking shorthand notation, I'm thinking the longhand notation. And the question that this is asking is the base e to what power is 1? And because anything to the 0 power is 1, That's why the answer to this is 0. The second problem, this number 8, I could also do without my calculator. If I'm using my calculator, I'm just going to hit the ln button, and then I'm going to hit shift and ln to get an e with an exponent. Then I'm going to type the number 2, close out my parentheses, and I get perfectly a 2 for an answer. If I was working without my calculator, the shorthand notation doesn't help me understand the question so much. If I was working without my calculator, I'd use this version of the problem. They're both equal to each other. On my calculator, if I did the log base e of e squared, it's still going to be 2 because the log base e and ln are interchangeable, but by hand it's easier to know the question when you can see the base. The question that problem 8 is asking is the base e to what power is the argument e squared? And the reason the answer is 2, because if I change that x to a 2, I get the statement e squared equals to e squared, and that's true. Those two I could do without my calculator. I'm completely content with you using your calculator to do those. The next two I couldn't really do very well without my calculator. It would take me, the better part of an hour to try to muddle through an answer. So I'm just going to do them quickly. The natural log of 4 is 1.386. The 6 in the third position tells me to round that 8 up to a 9. So I'm going to write 1.39 for my answer. I'm going to write a squiggly equals just because it's an approximation. So I can tell that's a rounded answer, not an exact answer. And my choices were either writing 1.38 or 1.39 for an answer, because the number in the second decimal place is an 8. When you're rounding the 2 digits, you either leave that number or round it up. The number after the 8 was big enough to tell me to round up. The next one I might get a negative number, the natural log of 0.3. I get negative 1.203, and again, the number in the third decimal position tells me not to round the 0 up. I'm going to leave the 0 alone. So for an answer, I could write negative 1.20, because that's technically rounding to 2 decimal places. But I don't really have to write the second decimal when it's a 0. So negative 1.2 would be equivalently fine answer. So far, the first 12 problems are just completely calculator problems. The next few problems are graphing problems, which are also going to be completely calculator problems. I forget what section, but a few sections ago we graphed problems that had x's in the exponent, and we were able to leave those problems unchanged. When we graphed logarithms, we had to tweak the problems. So there's 2 styles of graphs that we've done so far in this chapter: graphing exponent functions, exponential functions, and logarithmic functions. When we do exponential functions, I look at the exponent, I change the sign of the number in the exponent, and in this case the exponent has a positive 3. I'm going to change that sign from positive 3 to negative 3, and then keep my x's going so that I can get 5 consecutive numbers with a negative 3 in the middle. So the table I'm going to use is negative 5, negative 4, negative 3, negative 2, negative 1 in my x column. And then I'm going to have my calculator give me the y's. They're all going to have horrible decimals, and I'm going to round it 2 decimals and just going to have to approximate on my graphing. So now I'm going to do my table. So mode 7 for table, and then e with an exponent. So shift ln, e with an exponent, alpha x plus 3, start at negative 5, end at negative 1, step 1. So I get negative 5, and then I'm going to round that to 0.14. That's 0.1353, and then that I'm going to round to 0.37. Probably rounding to 1 decimal would have been more than enough, but 0.367 I'm going to round to 0.37. And then I get the point negative 3 positive 1, and then I'm going to get the same y. I'm not going to get that. It's not a parabola. I'm not going to get the same y's. Then 2.718, which I'm going to write as 2.72. And then the last one, 7.39 I'm going to write. So we're not getting duplication in the y's because it's not a parabola. In parabolas you get duplications in the y's. In exponential functions you don't. And now the best I can, I'm going to graph these points. So I need my y-axis to kind of go up to maybe up to 8. And then I'm just, it's not going to be a beautiful graph, but it's the best I can do. So -5 for x, that's easy to find. 0.14 for y, that's going to just be just barely above the x-axis. That's a positive number. That's a tenth of the way between the origin 0 and 1. And then -4.37, I go to -4 on the x-axis, and I go up a third of the way between 0 and 1. And then -3, 1. -2, 2.72, so I get somewhere between the 2 and the 3, a little bit closer to the 3 on the y-axis than the 2, and then -1, 7.39, somewhere in between the 7 and 8, a little bit closer to the 7 than the 8. And these graphs, they keep going up forever. They don't have an asymptote when they're going up, but off to the left, this graph is going to get super close to the x-axis. It's never going to touch nor cross the x-axis. It'll always be microscopically above the x-axis. So that's a reasonable picture for 14. I'll do 16 and 18 as well. And again, they're not that hard for me because it's easy for me to get the tables. 16, if I wanted to graph it, it's a nice exponential function. On my graph, I change the sign of the exponent when there's adding or subtracting in the exponent. The table that I use is based on the number in the exponent with its sign changed. So I found -2 on the x-axis, made a couple numbers to the left of it, a couple numbers to the right of it, so I can see 5 numbers with the -2 in the center. So I'm going to have -4, -3, -2, -1, and 0. You'll find out that when I do the tables like I do in exponential functions, the y's start to repeat themselves because the problems are kind of structurally the same. So when I do this now, mode table f of x equals shift ln for e, and then alpha x plus 2, start at -4, end at 0, step 1. You'll see a lot of duplication in the y's. So I get 0.14 x to the -4. And in the last problem, I did do 0.14, okay. And then 0.37 next to the -3, same y's. 1 next to the -2, 2.72 next to the -1, and 7.39 next to the 0. Same y's, different x's. You'll learn something about that in college algebra that has to do with shifting graphs and transformations of graphs. But I don't want to get into that just yet, but it'd be nice if you noticed that the y's are the same. It's going to become important in Math 151 if you're taking it next. So -4.14, because the 0.14 is positive, I find -4 on the x-axis, and I have to go up because it's a positive, but it's a small number, so it's really close to the x-axis. Next one, -3.37, I go to -3 and then up about a third of the way between 0 and 1. -2 and 1. -1, 2.72, 2.72, somewhere between the 2 and the 3, but closer to 3. And then 0, 7.39. 7.39 is between the 7 and the 8, a little bit closer to the 7. And the shape is the same. On the left-hand side, the graph always stays microscopically above the x-axis, but it keeps getting closer and closer to the x-axis to the point where at some point you can't distinguish the graph and the x-axis because it gets so close you just can't even draw that closeness. And on the right it goes up forever. 18, same deal. I'm going to get my starting table. I take the number in the exponent and I change its sign. It was a -3. I'm going to change it to a +3. And then I need 5 consecutive numbers on the x-axis with the 3 in the middle. So the table I'm going to use is the table 1, 2, 3, 4, 5. And the y's are going to be the same again. So I'm going to go mode 7 for my table, shift ln, and then alpha x minus 3, start at 1, end at 5, step 1. I get the same 0.14, this time next to the 1, the 0.37 next to the 2, the 1 next to the 3, 2.72 next to the 4, and 7.3739 next to the 5. So I have all my y's and x values. I'll plot the points. The graph's going to look the same. It's just going to be in a different location. So again, on my y-axis, need to get up to that 8. So 1 comma 0.14, go just above the x-axis at 1. 2 comma 0.37, I go up a third of the way between 0 and 1 at 2. 3, I go up to 1. 4, I go up to 2.72. 5, I go up to 7.39. And structurally, the graph is the same. It gets real high on the right, and on the left, it gets closer and closer to the x-axis, but doesn't cross nor touch the x-axis. So that's exponential functions. We graphed exponential functions a few sections ago. And even if the base wasn't an e, if this was y equal 2 to the x minus 3, my y's would be much nicer and easier to graph, but I do my table the same way. When the x is in an exponent, I change the sign if there's a sign and help that to get my table. Logarithms aren't as fun to graph. For logarithms, which we just did in section 6.4, I think I'm only going to do 2. Let me only do 20. Well, debating. I'll do 20 and 22 for certain, and then I'll debate how much further I go. So the first thing when I'm graphing logarithms, which ln is a shorthand for log base e, is first I'm going to find the domain. And just like we did logarithm graphs in 6.4, you find the domain by taking the argument of the logarithm, in this case, x minus 1, set it greater than 0. This is going to give me the domain as x is greater than 1. And that's going to show up on my graph very distinctively in that, probably screwed up here to give myself enough room, in that the graph is only going to exist because it's greater than, it's only going to exist on the right side of that line. And over here, there won't be any graph. So that for every logarithmic function, the first thing I do is decide where my graph will and won't exist. The nice thing about logarithms is I use the same table, but before I get ready for table mode, I need to write the problem without the logarithm. So first I did my table, and then second, I write the problem without the logarithm. And to do that, I need to use the equivalent form of the log base e, because I need to see the base when I write a problem without a logarithm. And to do that, I'm going to scratch out the log, the e is going to remain low, and I'm going to switch the y and the x minus 1. So doing that, cross out the log, the e stays low, I switch the y, and the x minus 1, that's what I mean for that. So I get x minus 1 equals e to the y. Usually we solve these for x. It makes it easier on my calculator, so I'm going to add 1 to both sides. I get x equals 1 plus e to the y. And then I don't use the table feature on my calculator because it's a little confusing. But for every logarithm problem, and an ln is a logarithm, I use the same starting table, -2, -1, 0, 1, 2, but in the y column. And now I'm going to get my y's. For the first one, I'm going to go, so get out of this table mode. Mode 1 would be fine. I'm going to go, first one I'm going to go 1 plus e to the -2, and then I'll do 1 plus e to the -1, 1 plus e to the 0, 1 plus e to the 1, 1 plus e to the 2, all on my calculator. So 1 plus shift ln to get an e with an exponent, -2. That equals 1 point, I'll say 1/4 rounded to 2 decimal places. And the next one I'm going to go 1 plus shift e to the -1. I get 1.37. Starting to see some similar numbers, kind of. And then 1 plus e to the 0 is going to be 2. And this should be, oops, yeah, and then 1 plus e to the 1 is 3.72. And then 1 plus e squared is 8.39. So now I'm going to plot these points. The first point, so on the x-axis I need to make it out to 9. So 2, 3, 4, 5, I'm going to start scrunching, 6, 7, 8, 9, best I could. 1.14 is just to the right of this dotted line, and then -2, so it's going to be down here. So I find 1.14 on the x-axis, and I go down 2 on the y-axis. 1.37 is kind of a little bit, a third of the way between 0 and 1, between 1 and 2. Then I go down to -1. 2, 0 is easy for me to graph. 3.72 is somewhere between the 3 and the 4, a little bit closer to the 4, and then I go up to 1. And then 8.39 is somewhere between the 8 and the 9, a little closer to the 8, and then up to 2. The logarithm graphs generally have the same shape, where they go down when they get to the asymptote and slowly work their way up to the right. So I know that I can't remember having a graph with an E or an ln on a test in many, many years. So the probability is low that you're going to see these in my test, but when you take Math 151, if that's your next math class, you'll definitely see these, so they're good to see. So 22, same style of problem, it's graphing a logarithm. So first I find the domain, and that's going to tell me where the graph isn't and isn't going to exist. So I'm going to go x plus 3 is greater than 0, minus 3, minus 3. The domain is x is greater than -3. So on my graph, that's definitely going to show up. I'm going to find -3 on the x-axis, and greater than -3 means to go to the right. So this is really a classic logarithm graph. There's going to be no graph to the left of that dashed line. Now I'm going to write the problem without the log. To write it without the log, I have to write the longhand form, the log base e, because that makes it easier to write without a log. I'm going to scratch out the logarithm. I'm going to leave the e low. I'm going to switch the y and the x plus 3. And then I'm going to minus 3 from both sides. So I'm going to get x equals -3 plus e to the y. And then for my table, The nice thing about logarithms is I use the same table for every logarithm graph. I'm going to use a -2, -1, 0, 1, 2, but on the y columns as opposed to the x columns, which makes it so my calculator's table kind of messes me up. Now for each one of these, I'm going to go -3 plus e to the -2, -3 plus e to the -1, -3 plus e to the 0, -3 plus e to the 1, -3 plus e to the 2. I'm going to get all my y's and round them to 2 decimal places. So first one, -3 plus shift ln e to the -2. I'm going to write -2.86, and then -3 plus shift ln e to the -1, and I get -3.37, and then -3 plus shift e to the 0, I get -2, and then -3 plus shift e to the 1, I get -0.28, and then -3 plus shift ln e squared, I get 4.39. I'm just going to plot all those points. They're a little tricky to plot, but not horrible. The first point, -2.86 on the x-axis, is real close to that dashed line. It's in between the -2 and the -3, and then I have to go down to -2. And then I find, I had to make a mistake. This is probably -2.37. Let me redo that one. -3 plus shift ln e to the -1. It's 2.63. I don't know what I was doing here. -2.63. So I did something wrong on my calculator, and I could tell because that point was going to be beyond the dotted line. That's not good. So -2.63 is a little bit about a little bit past halfway between -2 and -3, then down to -1, then -2, 0, and then -0.28 is close to the 0. It's just off the origin, and then up 1, and then 4.39. 4.39, a little bit past 4, up 2. And most logarithm graphs kind of have this feel unless the base is a fraction. I'm going to skip 24 but do 26, and if you wanted to skip through me doing that, it's fine, but it has a trick in there that's kind of nice to see, a trick that I'd never put on a test, but a trick that would be nice to be worried about in college algebra. So 24 and 26 both have the same trick. I don't ask logarithm graphs on the test, and let me do the 26 because that's probably more classic in terms of what you're going to see. So it's the domain part that's a wreck here. So to do the domain, that's what you do first for any logarithm graph. I set the argument greater than 0. I'm going to solve for x, and I'm going to leave the x on the left-hand side because it's going to help me. So I'm -2 from both sides. That gives me -x is greater than -2. And that really means -1x is greater than -2. The big trick to this problem, when I'm solving for x, I have to divide by a negative. And when you're working with less thans or greater thans, when you're working with inequalities, if you have to multiply or divide by a negative when you're solving for the letter, you have to flip the direction of the inequality. So this right here causes me to flip the direction of the sign. That's the trick to this problem. I get x is less than 2 as opposed to greater than. That's going to show up very differently on my graph. So when I get into graph mode for this problem, I should leave myself more room than that. When I get into graph mode for this problem, I'll pull out my graph paper. The graph is only going to exist to the left of 2. So pictorially, the domain that has a less than in it, I find that number on the x-axis and draw a dashed line through it. But x is less than 2, that means the graph is only going to exist to the left of the dashed line. And to the right, because the domain's not a greater than, that's where I'm not going to have a graph. Now I'm going to put it in logarithmic form and get my table, and then I'll graph all the points. So in logarithmic form, I get rid of the logarithmic form. I get y equals the log base e of 2 minus x. I'm going to cross out the log. I'm going to switch the y and the 2 minus x. So I get 2 minus x equals e to the y. I need to solve for x. I really don't like that x being negative, so I'm going to do this in kind of 2 steps. To solve for x here, I'm going to add x to both sides to make the x positive, and I get 2 equals x plus e to the y, and now I'm going to minus e to the y from both sides. So I get 2 minus e to the y equals x. And the table that I'm going to use is still the same -2, -1, 0, 1, 2 table. And I'm going to go 2 minus e to the -2, 2 minus e to the -1, 2 minus e to the 0, 2 minus e to the 1, and 2 minus e to the 2 to get my y values. So there's double tricks on this problem. Again, I wouldn't put these tricks on the test. Knowing the rules of inequalities, when you're solving an inequality for a variable, if you're dividing by or multiplying everything by negative, you have to switch the direction of the inequality. That's the first trick. And then even when I shoved it in the logarithmic form, it was without the exponential form without the log, it was a little tricky too. So I'm going to do all these points on my calculator now. So first one is going to be 2 minus shift ln e to the -2, and I get 1.86. And I probably could just go backwards, change the -2 to a -1, and I get 1.63. Could just arrow backwards again, delete the -1, delete the negative sign, type in a 0, and I get, lovely, I get 1. And then backtrack again, change the 0 to a 1, and I get -0.72. And then backtrack again, change the 1 to a 2, and I get -5.39. So I'm going to plot these points the best I can now. First point, I go 1.86. 1.86 is close to 2, and I go down 2. So that's about the point 1.86, -2. And then 1.63 is real close to 1.86, but it's a little to the left of it, and then down 1. 1, 0 is here. -0.72 on the x-axis is, somewhere between the 0 and the 1, but I need to go up 1. And then -5.39 is about there, and then up 2. And so my graph looks like this. And it fits perfectly with what I wanted it to fit in terms of where there was a graph and where there wasn't a graph. So if you watched that, thanks. If you didn't, it's okay. And if you completely don't understand that, come visit me and I can sit down with you and try to explain it in a little more detail. I don't know if I went a little too quick there, but it's not something that we're worried about. So the last things we need to do are some money word problems, and they're easy word problems, but they have a new formula. So a few sections ago, we did money word problems, and we had a formula that I'll revisit. So this is just a review. Two pieces of paper. So to review money. So a few sections ago we did problems like this. This is a review problem, not from the section. I just want to refresh your memory. An investment of $2,000 earns 4% interest compounded monthly. What will the investment be worth in 10 years? This could definitely make its way into the test. So it's a good time to review it. So in order to solve this question, we needed to remember the formula that we used. The formula that we used a few sections ago is A equals P times 1 plus R over N to the NT power. The P was the starting amount of money. In this case, it's going to be $2,000. The R in the formula was the interest rate as a decimal. In this case, it's going to be 0.04. The N was always clued into by the word after monthly. And the N is the number of times you get interest each year. Since interest is being paid monthly, the N is going to be 12 because there's 12 months in the year. And the T was the number of years. In this case, it's going to be 10. So to find the amount of money I'm going to have in 10 years, I'm going to plug the 2,000 in the formula for P. I'm going to plug 0.04 in for the R. And I'm going to plug 12 in for both of the N's. And 10 in for the T. So this is review. And for this problem, to do it on my calculator, I just need to go 2,000 parentheses 1 plus fraction 0.04 over 12 to the 12 times 10 power, and I have to round it 2 decimal places because it's money. I get $2,981, and I'm going to round that to 67 cents. So that's review. If you look at the problem 28 that we have to do next, and the problem that I just did, they're worded the same way, but they have a word that might be new to you mathematically. Continuously, it's not like a new word, but in mathematics, that means, for interest purposes, it means I'm getting interest more than monthly, more than once a month, more than once a day, more than once an hour, more than once a second. I'm getting interest every, more than every 1/1,000,000th of a second. I'm constantly getting interest. And when I see the word compounded continuously, that means the n is equal to infinity. So if I wanted to do this problem using the formula that I'm comfortable with, I would say P is the beginning amount of money, which is 5,000. R is the interest rate as the decimal, which is 0.06. N is the number of times I get interest each year. Continuously means I get interest infinitely many times. And T is the number of years. So I would do this. I would try to go, the amount of money I'm going to have in the future is 5,000 times 1 plus 0.06 over infinity to the infinity times 5 power. That would be just plugging the numbers into the formula perfectly. And then if I tried to do that on my calculator, I couldn't because my calculator doesn't have an infinity button. The best I can do is like when I was playing around with E, start putting large numbers in for infinity. The larger the number I choose for infinity, the closer my answer is going to be to the correct answer. So the best I can do with the formula that I have is guess and get an answer that's close, but maybe not accurate. if you look at the what I'm attempting to do, and remember the E formula, E is 1 plus 1 over infinity to the infinity power, you can almost start to see that. I see a fraction with an infinity in the denominator. I see an infinity in the exponent. It would take calculus to show it, but when the n is infinity, I can't use my calculator with the regular compound interest formula. There's another formula that mathematicians have developed with an E in it, because this formula looks like the E formula, and I have to use the E formula to solve the problem. So for each problem 28 and 30, because I can't put infinity on my calculator, there's a new formula. So there's the regular formula that we had, A equals P times 1 plus R over N to the NT. This formula will not work for this problem because the n is infinity. I can't use it. When interest is compounded continuously, means the n is infinity. There's the formula up there I have to use, and it doesn't have an n in it. And the E kind of gives me the infinity. The infinity that I needed in the formula is kind of embedded in the computation for the E. So to solve both problems 28 and 30, I'm going to use the amounts that I can type into my calculator. The beginning investment of $5,000, the interest rate of 6%, and the time of 5 years. And the E is going to help. It's going to give me the infinity part of this. So to answer this question, I'm going to go the amount of money I'm going to have in the future will be equal to the initial amount of money, $5,000, times E to the 0.06 times 5 power. I'm going to round to 2 decimals. So if I did this on my calculator, I'd do 5,000 and then shift an ln to get an E with an exponent, and the exponent's 0.06 times 5. That's going to be the answer. And I'm going to round to 2 decimal places. So I see 29.4 cents. I'm just going to round to 29 cents. So the answer to problem 28 is, in 5 years, my $5,000 is going to grow to $6,749.29. I'm going to do problem 30. And any money problem that we're going to be given, I immediately have to look to the word compounded. If after the word compounded is continuously, I need to use the E formula. If there's another word after compounded, like monthly, quarterly, semi-annually, daily, I use the formula with the N, because the word after compounded tells me what the N should be. Monthly would be 12, quarterly would be 4, daily would be 365, but continuously means the N is infinity, and when the word after monthly, after compounded is continuously, I have to use the E formula. And the E formula is easy to use. It's just actually probably easier for me on my calculator to use the E formula. So immediately, this was a money problem. I saw the word continuously. I know I'm using the E formula. And in the E formula, I only need three letters as opposed to 4. I need the starting amount of money, P, which is $25,000. I need the interest rate in decimal form, which is 0.04, and I need the time, which is 11 years. So the amount of money I'm going to have in 11 years can be computed by changing the P in the formula to 25,000, leaving the E alone, changing the R to 0.04 and the T to 11. So I'm going to go 25,000 shift E 0.04 times 11. I'm going to round to 2 decimal places. So I get, in 11 years, my $25,000 is going to go to $38,817. And I'm just going to round to 68 cents. It's a money problem, so I should round to 2 decimal places. And since the number after the 8 in the 3rd decimal place wasn't big enough, I didn't round up. So again, so just to be clear, in 28, I'm going to end up with that $6,700. And in problem 30, I'm going to end up with that $38,000. So those are still in the easy word problem kind of genre, I guess. We have some more money word problems coming up in 6.7, and they're a little bit tougher than the word problems that we've been exposed to so far because the way they're worded. And once we get to those, I'll explain to you why they're more difficult and how do we go about solving them. But so far, the only word problems that are test worthy are all the money word problems, and if you just have the correct formula and know the numbers that need to be plugged into the letters, it's just a calculator problem. So they should be moderately friendly so far. Alright, so just 2 sections left. 6.6 and 6.7 are longer sections, so be prepared, especially 6.7. It's a very long section. I might split 6.7 into 2 videos, just because if it's starting to feel like it's getting insanely long, I'll split it into 2 videos. So be prepared for some long sessions and just have lots of time dedicated for 6.6 and 6.7. The stuff in there is really important. It's weighted kind of a little heavier on the test than the beginning of chapter 6, and it's super important if you take Math 151 next.